So we are learning about impulse and momentum today. Now, when Newton first came up with his second law, what is Newton's second law, by the way? Come on, you guys know Newton's second law. What is Newton's second law? I'm going to pick on somebody. Victoria, what's Newton's second law? Someone help her out. What is Newton's second law? Alexandra?
Mass times acceleration.
Yeah, force is equal to mass times acceleration. Now, when he first came up with this, he actually defined it in terms of velocity. So I'm going to derive right now for you your equations of momentum and impulse. Now, what is acceleration equal to? What is acceleration equal to? If we were using Newton's second law, correct. But when we learned about, at the start of this semester, how did we define acceleration?
Change in velocity over change in time.
Excellent, Omar. It's going to be a change in velocity over our change in time. Now, if I substitute this in for acceleration here, what do we get? We get force is equal to mass times the change in velocity over time. And if I move t over, time over, by multiplying both sides by t, I get force times time is equal to mass times our change in velocity. So I derived this from Newton's second law. Now, these values here are impulse and momentum. So momentum is this here, mass times our change in velocity. In particular, this is actually going to be our change in momentum. Because we'll talk about defining momentum in a second. So this is going to represent our change in momentum. So our formula for momentum is going to be our mass times our velocity. And we often will represent momentum as P. Our formula for impulse is going to be what? It's going to be the other one. It's going to be, what? I heard it.
Force times time?
Yeah. Our impulse is going to be our force times time. Or help if I can spell. Impulse. So what do you think the units are for momentum? Oh, by the way, impulse, some places you're going to see it written J, others you'll see it written I. What are the units for momentum? Think about it. What are the units for momentum? When we use Newton's second law, what are the units for acceleration here?
Meters per second squared.
Meters per second squared, right? So if we,
Morning, Mr. Saul.
good morning.
Hey, I guess Faye's not here today.
Oh, okay, thank you. Good morning.
I still, all of the substitutes for the EAs always still go to 108.
Oh no,
Yeah.
they didn't change that on the schedule, that's brutal.
Yeah.
Okay, so, where was I? acceleration, we measure that in meters per second squared. Thus, our velocity here is going to be meters per second. So what is going to be our units? How do we measure mass in which units? Kilograms. So our units here are going to be in kilograms meter per second. What is going to be our units here for impulse? What are our units for force? Newtons. And how do we measure time? How did we measure it for Newton's second law? In seconds, yeah. So it's going to be Newtons times seconds. All right, so that is your equation for impulse. That is your equation for momentum. Keep in mind, though, when we're talking about impulse and momentum, your impulse, J, is going to be equal to your change in momentum. All of this will become a lot more clear as we do some examples. Let's define now what momentum is. Just looking at our two variables, though, how would you define momentum? Someone take a stab at it. How would you define momentum? So momentum is defined as mass in motion. Quite literally the units, or the variables, sorry, of momentum. So if an object is moving, does it have momentum?
Yeah.
Yeah, right? So we'll say if an object is moving, it has momentum. And what does the amount of momentum depend on?
The mass.
And?
The velocity.
The mass and, you had it?
Velocity.
And the velocity, excellent. So it depends upon two things. It depends on how much stuff is moving. And we call that mass, right? How much stuff is moving, and how fast that stuff is moving. Is moving, which we call velocity. Now, is velocity a vector? Is velocity a vector? Yes, it is. So momentum is a vector as well. Momentum is a vector as well. So what is going to be the direction of your momentum, do you think? Will it be the same as my direction of motion? Yes, it will, right? So momentum is a vector. So momentum is a vector. And the direction is the same as the direction of motion. Alright, so that is momentum in a nutshell. So it is mass in motion. Now do not confuse this with inertia. What is inertia? Changes in velocity, yeah. The tendency of an object to resist changes in velocity, aka resist acceleration. Now what is the determining factor when it comes to inertia? What is the only quantity that matters? Mass, right? Mass. So don't confuse these things, because if I have a really, really heavy object that isn't moving, does it have inertia? Does it have a high inertia, really massively? You have a giant train, right? It's not moving. Does it have inertia? Yeah, right, it does. Inertia is just a property of mass. But does that train that's not moving, does that have momentum? Why not?
Because it's not moving.
Yeah, because it has no velocity. It's not moving, right? So it has no momentum. Students will often confuse those two things, so just be careful in your thinking. All right, so that is momentum. Now, what is impulse? What is impulse? Well, what does your formula say impulse is? Sorry? No, you're right. What is it? Come on, Basola. Okay. What is your formula for impulse say? Force times time. Now, in particular, this is going to be a force applied over a length of time. So, impulse. We're going to explore this through the lens of stopping an object. So, in order to stop an object, we will have to apply a force If we apply an unbalanced force, what's that going to do? What does an unbalanced force cause? Sorry? Gordon? What does an unbalanced force cause? Not necessarily. It's going to cause it to slow down or speed up. What do we call that? Starts with an A. Yeah, it's going to cause acceleration. Now, if I applied, let's say I'm trying to stop a car, and I just tap the brakes for a brief instant in time. Is that going to stop your car?
No.
No, why not?
Because it's only going for like a second.
Yeah, I only applied that unbalanced force for a brief moment in time. What do I need to do?
Hold it down for
I need to hold down the brake, right? We have to apply that force over some period of time to stop the car. So, in order to stop an object, we will have to apply a force which causes an acceleration, in this case a deceleration, over a period of time. Do you think an object with more momentum will take more force over time to stop?
Yes.
Yeah, intuitively you know that, right? Like a car traveling 10 kilometers an hour is a lot easier to stop than a car traveling 100 kilometers an hour, right? 100 kilometers an hour, you have a lot more momentum. So, let's write that down. Let's say the more momentum an object has, the harder it will be to stop. And by harder, what do I mean? What am I going to have to do?
Apply more force.
I'm going to have to apply a larger force, or what else could I do?
Hold it down for a longer time.
Increase the amount of time I apply that force. So, therefore, it would require a larger force or greater amount of time or both to stop. Because remember, when I wrote those equations down, when I wrote those equations down at the start of class, your momentum was equal to what? Your change in momentum is equal to what? What did you write down there? Well, that is your momentum is mass times velocity, right? Your change in momentum is going to be your mass times your change in velocity. But what is that equal to? Was it equal to force times time? Yeah, it's equal to your impulse. That's right, it's equal to your impulse. So your change in momentum is equal to your impulse required. Now, this here, the amount of force or the amount of time, that is what we call impulse, right? Now, let's go through some examples here. In order to change momentum, we must apply an impulse. For example, who here plays soccer? I know there's a couple of you in the room, or just one of you in the room. So if I wanted to kick a ball, what would your coach say to you? If you want to kick the ball really hard, what has your coach told you to do in the past? Who here has played baseball? A couple people play baseball. If you want to hit the ball really far, what has your coach told you to do?
Swing really hard.
Swing really hard? Is that all he said? Or she?
Focus on the ball and swing really hard.
Just focus on the ball and swing really hard?
Yeah.
What would happen if I was trying to hit the ball and I just did this?
It'd go nowhere.
Why?
Because you don't have any follow through.
That's the word I was looking for. I have no follow through, right? Why is it that I want to follow through when I swing at a ball? Or why is it when I kick, I want to follow through on my kick to kick the ball really, really hard?
To apply more force.
Sorry?
To apply more force.
Not necessarily to apply more force. Not necessarily to keep the momentum. You're going to be radically changing that object's momentum, right? When you hit a baseball, you're radically changing that object's momentum. It's coming at you, and then what direction is it going after you hit it? Away from you, right? You are changing the direction of that ball, and it's going to be going a lot faster once you hit it. Why is following through important? It's really important in golf, in all sports really, in tennis, in golf, take your pick. You have to follow through if you want to get any power. what are you doing when you follow through? Let's use a different example. Anybody here a boxer? This is so I don't know, maybe someone's a boxer in this room. How am I supposed to know? Have you ever heard roll with the punches before, the saying? Yeah, some of you are shaking your head. Yes, yes, yes. It's actually a proper technique in boxing. Why is it that if you get punched in the face, you don't want to just like take it head on? You want to take that punch and roll with the punch. Okay, well, let's. Do you have an answer for me there, Kiara?
I don't know, so like you absorb the force.
Interesting. This comes down to a really fundamental idea. So why do we follow through? Well, we follow through because we are going to be increasing the amount of time that that ball is in contact with your foot or in contact with your baseball bat or your golf club, right? And by increasing the amount of time, what are we doing to the impulse? Right? The force that you're hitting that ball with is pretty constant throughout that contact time. Right? So that force isn't changing much. But by following through, you're going to increase the contact time. What is that going to do to your impulse? What's that?
Greater impulse.
Yeah, you're going to increase your impulse. And remember, your impulse is equal to your change in momentum. So if we increase the impulse, what are we doing to that object's momentum? Well, if we increase this, is this also going to increase? If they're equal to one another, that has to increase. So when you follow through, your baseball is going to have more velocity. Your soccer ball is going to have more velocity, right? Your golf ball will have more velocity. Take your pick. So by increasing the amount of time you are in contact with that object, you are going to increase the impulse that object experiences, and thus that object will have a greater change in velocity. So let's kind of write that down. So in soccer, let's say, baseball, golf, etc. It is important to follow through. As this increases, the time over which the force is applied. And is that going to cause a greater change in momentum?
Yes.
Yeah, it will, right? So, therefore it will increase our impulse, which increases our change in momentum, right? Because those two things are equal to one another. And therefore our ball here will have a, therefore, greater velocity. Right, so that's why following through in sports is so important. You want to extend as much as possible that contact time such that that force can be applied over a greater period of time, increasing that change in momentum and therefore its velocity. Now let's go back to the boxing example. Let's go back to the boxing example for a second. Now, when you punch somebody, let's say I'm really angry at Ben here and I punch him in the face. Does my fist come to a stop?
No.
If I punch him in the face, is my fist going to come to a stop eventually?
Yes.
Yeah, it will, right? It's going to come to a stop. So is the change in momentum here, is that going to be the same no matter what happens?
No.
Yep.
Yeah.
Pretty much, right? If I'm throwing a punch with some velocity and some mass, right? Because what is momentum? What's the formula for it? Mass times velocity. So I'm throwing a punch with some velocity, okay? And no matter what happens, when I punch in the face, my fist is going to come to a complete stop. So my change in momentum is constant. So does that mean my impulse will be constant as well? That number, will it always be the same? Right? Because they're equal to one another. So if this is always the same, this is always the same too. So think about that. Why is it that you want to roll with the punches as opposed to just taking that shot head on? Why is it better to do that? Think about it. Your impulse isn't changing, but what can change? What are the two things that make up your impulse? Force and?
Time.
Force and time. So what could you change?
How much time you're getting punched.
Yeah, how much time my fist is in contact with your face. So if I increase the amount of time, what happens to the force as a result? It'll go down because your impulse isn't changing, right? That's why it's better to roll with the punches, because it'll decrease the amount of force your face experiences, which is fantastic, right? If you eat that punch head on, my fist is going to decelerate really quickly. It's going to take a very brief instant in time. So what's going to happen to the force?
It's going to be exerted on your face.
It's going to be way higher on your face, and it's going to suck, right? So that idea is a fundamental principle in car crashes. That is a fundamental idea in car crashes. So if we look at a car crash, what are some things that vehicles have to save your life?
Airbags.
Airbags is an excellent example. So let's look at vehicle safety for a moment. We have airbags. What else? Seatbelts. We're not going to talk too much about seatbelts right now because that's more of a Newton's first law, right? Object stays in motion situation, right? What was the big difference that happened from cars, say from like the 70s to now? My buddy had a crazy boat of a car, all rigid steel frame. When in the winter, he used to like just drive that thing into snowbanks, and no matter what he did, that car would not break or bend at all. Like the car would not even get a dent when he crashed into a snowbank. Whereas if I did that with any modern vehicle, what would happen? Yeah, it would break. It would crumple up. You would have tons of damage. Why is that? Why are vehicles just built cheaper now? Why is that? We call this crumple zones. What do you guys think? Is this an intentional design decision, or is this just because vehicles are cheap nowadays?
Intentional.
It is intentional. It is intentional. What do these things do, airbags and crumple zones? Keep in mind, let's lay out a scenario here. In an accident, your car will your car will have a a constant change in momentum because it was going from some velocity to 0. Right, it had some sort of constant momentum, right? The momentum change is constant here. Now, what is your change in momentum equal to? It's equal to what? Yes. Since your change in momentum is equal to your impulse, that means that your impulse must be the same. So how is it then that airbags and crumple zones save your life? This is a fundamental question. It's going to for sure be on your unit test. How is it that airbags and crumple zones save your life?
Because they absorb all the force that's applied.
That is the most common answer I get on the unit test. And I would say that that is incorrect. Intuitively, that's the way we think about these things, but that's not the reason why. What's actually happening? Think of the rolling with the punches example. Think of the rolling with the punches example. So this is the big question. How is it that these features save your life? You had a great answer there, Nick, for the rolling with the punches. How is it that rolling with the punches makes your face not take as much force? What are you doing?
Oh, the time.
The time. So by having airbags and crumple zone, what are we doing? Think about it. Airbags. You are going to hit this airbag and it's going to gradually slow your head down instead of smashing against the steering column. So what are we doing to the amount of time there?
Increasing it.
We're increasing the amount of time it takes for the change in momentum to occur. And therefore, what happens to the force? It goes down. And what does an unbalanced force cause? Acceleration. So what's going to happen to the amount of acceleration? It also goes down, right? So acceleration is what kills you in an accident. The rapid change in acceleration, right? The rapid, we're going to talk about G's in a second, but when you hear like 10 G's of force, 100 G's of force, 200 G's of force, it's that acceleration that kills you in these accidents. Because if you slow down too quick, what's your brain going to do, for example? Your brain's in liquid. It's going to keep doing what it's doing. If it's traveling really fast and you stop immediately, what's your brain going to do? It's going to smash into the front of your skull and you're going to die. Right? So slowing down too quickly will kill you. And this was how people died by the droves with those early vehicles. Those steel frame vehicles were super unsafe. Right? Even low-speed collisions were dangerous strictly because you slowed down too quickly, increasing the force and thus increasing radically the acceleration you experience. So how does this save your life? Well, these features increase the amount of time over which the change in momentum occurs. And therefore reduces the force experienced by the passenger and thus their acceleration. Right, the rapid deceleration, because that's what kills you in an accident, right? The rapid deceleration is what kills you, right? A large acceleration is dangerous. Right, a large acceleration is dangerous. I've hit you with a lot of intense theory, so let's take a brief break here. Have you guys ever heard of Rocket Man? But he wanted to show that the human body is capable of surviving much higher acceleration. And we measure, acceleration in car crashes and stuff like that as G's. What is a G? You guys know what that means? Yeah, what is acceleration due to gravity? You know this number. What is it? Thank you. It's 9.8 or 10. We're going to just say whatever. Yeah, 9.8 meters per second squared. So if I say there was you experienced 10 G's in that accident, really, what was your acceleration? What would 10 G's be?
98 meters per second squared.
Yeah, it'd be 98, right? So when we're talking G's, we're really just talking, 10 G's would be 98 meters per second squared. We're really talking how much acceleration you experience. So he wanted to really show that the human body was capable of surviving way more than originally thought. And he successfully did so. In fact, his last run he did, the Air Force had to say, like, hey, buddy, we're putting an end to these experiments because you're going to kill yourself. Because the last rocket sled experiment he did, he actually was like blind for a week, was like bleeding from his ears, and it was horrible. He broke a bunch of bones. So this guy was legitimately pretty crazy. But he redefined what we thought was possible in terms of what the human body could handle. And as a result, safety belts were soon implemented, and safety features in cars began to arise. So a large amount of acceleration is extremely dangerous. The limit of what the body can handle before you die varies from person to person there. But after seeing that video, what acceleration did he achieve? How many G's?
46 point something.
It was like 47 pretty much. If it's 47 G's, what was his acceleration? We'll just say your acceleration is 10 meters per second squared. What was your acceleration?
470.
Yeah, 470. So that's an insane acceleration, right? And he was able to survive that, barely, albeit, but he did survive it. So let's look at a practical example using everything we've learned today. And this might melt your brains, so come back to it several times until you kind of fully understand this relationship between momentum and impulse. So let's say that, Mr. Salt here is driving an old car, a really old car. And no seatbelt, just complete disaster. I get into an accident and I slow down extremely quickly. So let's say in an accident, Mr. Salt goes from a speed of 100 kilometers per hour to a complete stop actually let's say, yeah, that's fine. Mr. Salt goes from a speed of 100 kilometers an hour to a complete stop in 0.01 seconds. Okay. If Mr. Salt has a mass of 72 kilograms, what is the acceleration he experiences? Now, some of the keen people out there, you might realize right away that I've given you your change in velocity and the amount of time it took. So how can we figure out that acceleration? What is the old way we learned how to figure out acceleration? What is acceleration equal to?
Change in velocity over
Change in velocity over time. So we can easily figure out my acceleration without any other information. But I wanted to do this a different way. Let's explore the change in momentum and the resultant impulse in this car wreck. So what is my momentum equal to? My change in momentum.
impulse.
Yeah, my impulse is equal to my change in momentum. And what's the formula for impulse? It's going to be force times time. And what's my change in momentum equal to? Mass times our change in velocity. Now, looking at this, we know all of these variables except for one. So, what is our time? Well, actually, let's isolate force here because that's kind of what we're interested in. Let's isolate force. So, what is our mass? 72 kilograms. What is my change in velocity?
100 kilometers an hour.
Yeah, since I didn't give you direction, would it be 100 kilometers an hour or negative 100 kilometers an hour? Technically negative. But when we're calculating our force here, that's not going to matter all too much. Because I didn't give you direction. And how long did it take for me to slow down?
seconds.
0.01 seconds. Now, as a result of this accident, how much force am I going to experience then? Right? Over that 0.01 seconds, what kind of force is applied to my body? That's going to be 72 times 100, 7,200, divided by 0.01 is like times 100 again. Does that look right? 720,000? Does my math check out there, Nick?
Hold up, 1 sec.
Ah.
Yeah.
So that's a really big number. That is a really, really big number. Now, if I wanted to know what my acceleration was based on this force, how would I figure that out? I'm doing a little review right now. How would I figure that out? What's your force equal to? Newton's second law. Yeah, remember your force is equal to your mass times acceleration. Therefore, my acceleration must be equal to my force over my mass, or 720,000 newtons divided by 72 kilograms, which gives me what?
2,000.
Yeah, 10,000 meters per second squared. How many G's is that? Well, if I divide that by 10, how many G's is that?
1,000.
Yeah, 1,000. Right? If I divide this by 10, that is 1,000 G's. Now, Paul Stapp, how much force did it, sorry, how many G's of acceleration did he almost die from?
47.
47. If he pushed it somewhere between, we think anywhere after 50, you're at serious risk of dying. Did I die?
Yeah.
Oh yeah, big time. I'm dead for sure. No question about it, I am dead. Now, what would happen, let's say, if I changed these numbers a little bit? Let's say now I'm driving a modern car, okay? I get into an accident, the airbags go off. The front end of my car crumples up as I get into an accident, right? All of those features will extend the amount of time it takes for me to slow down to a stop. And what happens to the force on me as a result?
Slow down.
So what's right? It decreases. So let's change these numbers. The only thing I'm going to change here is this. We'll say instead of 0.01 seconds, it took 1 second. Okay, so the airbags, actually it's probably unrealistic, but that's fine. We'll say 1 second. It'd probably be more like 0.25 or 0.5 of a second. But my airbags and the crumple zone on my car have increased radically the amount of time it takes to come to a stop. So what's going to happen then to the force my body experiences? If I increase the amount of time the change in momentum occurs, right, increase the amount of time over which that change in momentum occurs, what's going to happen to the force? It's going to go down. Right? My change in momentum hasn't changed. Right? If we look here, my change in momentum is 72 times 100 kilometers an hour, which is what?
Negative 7,000.
Yeah, so my change in momentum, right, is negative 7,200 kilograms. Oh, why did I screwed up, ladies and gentlemen. What did I do?
Convert the 100 kilometers an hour to...
Thank you. I didn't convert my 100 kilometers an hour. This is inaccurate. That's my bad. So, how would I convert 100 kilometers an hour to meters per second? Nick, in your calculator there, can you please divide 100 by 3.6? That is 200,000 on the nose. Still a big number. 200,000 newtons. $200,000 divided by 72 is 2,777.77 meters per second squared. Which means how many G's did my body actually experience? Sorry, I screwed up that math hard. 277.77, right? So, my bad. It was 277.77 G's, my body, not 1,000. Am I still dead?
Yes.
Oh yeah, I'm still dead. 100%. Has everyone fixed their numbers? Okay, my bad. So let's go back to my more modern car for a second. So the more modern vehicle takes longer to slow down. Remember, my change in momentum is constant, which it's not going to be 7,200. What is it going to be? Minus 2 zeros from this. Give me 2,000. Does that mean my change in, sorry, does that mean my impulse must also be 2,000? Yes, it does, right? Yes, it does. And that's going to be my force times a time of 1 second. So what must my force be in this situation? It's not going to be 200,000. What is it going to be? It's not going to be 200,000. What is it going to be? It's going to be 2,000, right? So by increasing the amount of time, we've radically decreased the force I experience. So if I change this to 1 second, 72 times 27.77777, that is 2,000 newtons. And what will be the acceleration I experience as a result of this? Well, that's going to be 2,000 newtons divided by 72 kilograms, which will be 27.77 meters per second squared, which is how many G's?
2.7?
Yeah, 2.78 G's or whatever. So that will be 2.78 G's. So am I going to survive that crash?
Yes.
Oh yeah, big time. Does that make sense, everyone? Yes? Okay. Sorry I screwed up those numbers there. So by extending the amount of time that this collision took, I have radically decreased the force experienced on my body. And that is how airbags and how crumple zones save your life.